Hello everyone, I am Ravi Shankar Pal from ABES Engineering College Ghaziabad. In this video lecture, I am going to explain about the calculation of three-dimensional address calculation of three-dimensional array of a particular location of an element. I am also discuss about the address calculation of n-dimensional array in this video lecture. So let's start. First, we know how to represent the three-dimensional array. Basically, three-dimensional array is also known as cube. So I am going to represent it in a very simple way. How to represent three-dimensional array, a matrix. Suppose if we can write A, 2, 3, 4. What is the meaning of this? Here, this is three-dimensional array A. There are three subscripts. Suppose if you have single subscript, means it is one-dimensional array. If it is to have two subscript, then it is known as two-dimensional array. And if it has three subscript, then it is called three-dimensional array. In one-dimensional array means there are two elements in memory, that is 0, 1. If you can represent this in memory, means there are three one-dimensional array and each one-dimensional array has four elements. Similarly, we can represent the three-dimensional array. What is the meaning of 2 is here? 2 represents the two-dimensional array and each two-dimensional array contains the 3 into 4 elements. 3 by 4, that is 12 elements. If we can represent this in matrix form, then we can write two-dimensional array, two-dimensional array that is of 3 into 4 size. This is the two-dimensional array and there are two-dimensional array and one two-dimensional array contains the size 3 into 4. Here 0, 1, 2 and 3. And if you write the index here, then it will, and another two-dimensional array similarly of same size 0, 1, 2, 0, 1, 2, 3, and this is also of same size here. And this is first, this is 0th two-dimensional array and this is the first two-dimensional array, means there are two-dimensional array and each two-dimensional array is of 3 by 4 size. If you represent the index in memory, then first you will consider 0th row, then inside the first two-dimensional array, here 0th row and 0th column, and second 0th two-dimensional array, in 0th two-dimensional array 0 row and 0 1 column. So 0 0 0 1, here 0 0 0 2, then 0 0 3, here 0 1 0 0 double 1 0 1 2 0 1 3, here 0 2 0 0 2 1 0 to 2, and 0 to 3. And this location is represented as first, that is second two-dimensional array, like zeroth row and first row. First you will write first, then this 0, then this 0. Again 1, 0 and 1. 1, 0, 2. 1, 0, 3. And this one is 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 2, and 1, 1, 3. This one is 1, 2, 0, 1, 2, 1, 1, 2, 2, and 1, 2, 3. These are the memory representation, index memory representation of A into 2 into 3. Now, if we want to find out the location of any particular element, if you want to find out the location of any particular element in this two-dimensional array, then how to find out it? Let's start. Suppose here we have represented an array 2, 3, and 4. Suppose we want to find out the location of this one, then this is represented like A, 0, 1, and 2. If you want to represent this one, then it is represented like 1, 2, and 3. And if you want to calculate the address of this element, then how can we calculate it? Let's suppose this is the mth two-dimensional array. There are total m number of two-dimensional array, and one-dimensional array contains n into p size two-dimensional array. And if want to find out the address of 1, 2, 3, then first one means you have to skip one two-dimensional, that is zeroth, and come to first two-dimensional array. Then how many element you have to skip? That is 1 into total element skip in this two-dimensional array is the 4 elements here. Then how can you know 4 elements? And there are 3 rows. Means you have skipped 3 into 4 elements, that is 12 elements. There are total 3 rows, and each row contains 4 elements, and these 3 rows is nothing but this one, and 4 elements is nothing but this one. So if you skip one two-dimensional array, you have to skip 1 into 3 into 4 elements. Plus now if you reach here in this location, then you have to find out the in this location again, then you will skip two row means this row and this row, and you will reach out this location. And if you will reach out this location, you will cross 1, 2, 3, 4. In each row contains 4 elements. Each row contains 4 elements, means 2 of this, 2 of this, and 4 of this original matrix. And plus if you reach out here, then you will cross 1, 2, 3 elements, and these 3 elements is nothing but the total number of columns in first two-dimensional array, means second two-dimensional array, that is 3, this one 3. Okay, So how many elements you have skipped? Skip here 12 plus 4 into 2, that is 8, plus 3, that is 23. Now we'll count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Means to reach here, you have to cross the 23 elements. So if you generalize this formula and you want to find out the address of a location I, J, K, basically in three-dimensional array, you have to also represent in memory in row measure order, as well as column measure order and column measure order. So first I am going to calculate, this one is row measure order. Okay. In row measure order, first you have to add the base address, and now you have crossed the elements. Generalize this. What is this? This is I. Then you have to cross the ith two-dimensional array. Suppose each element contains the each element contains the size of w bytes. We assume here ith row. Then what is 3 here? 3 is the here number of row of the zeroth two-dimensional array, means multiply by n, and what is 4? 4, that is column of two-dimensional array, that is p, plus what is 2 here? Jth, that is 2, this value j, j into number of columns. Each column represents the elements, that is 4, and what is column here represented, that is p. Okay. And if one element contains the size in memory w byte, then it will w byte. So this is the formula to find out the location in row measure order. If we represent the array like lower bound 1, upper bound 1, if this is m, size of m, and lower bound 2, upper bound 2, if you don't start the start index of row 0 or 1, and lower bound 3 up to lower bound, upper bound 3, means this is m, n, and p, then your generalized formula for row measure order is AJIK, that is base address plus I minus lower bound for m, that is LB minus 1, into n into p, n into p, plus j minus j minus j minus lower bound 2 into p, plus, here I have missed the k, here it is plus 3. 3 means this one, k also, then multiply by w, k minus lower bound 3. Now multiply by the size of one element. So this is the final formula to calculate the address of any location in three-dimensional array in row measure order. Similarly, if you want to calculate the address of any element stored at location I, J, K in column measure order, column measure order, then suppose your matrix is A, M, N, and of P size, and here you are going to find out the location I, J, K, and if lower bound of this is LB1, lower bound of this is LB2, and lower bound of this one is LB3, then in column measure order, you will find the location from left to right. Like first you will add the base address plus. Here first you will calculate the K minus lower bound of K is LB3 into. Here you will multiply, you will cross n into m, that is m into n elements, then plus. Now you will reach to j. J minus lower bound 2, lower bound 2 into cross m elements only, that is m, plus. Now we'll reach to ith element I minus lower bound of I is, that is lower bound 1, and here there is no element, so don't multiply by anything. Now this is the size of one cell, and if one cell size contains the W bytes, so this will the formula of column measure order. Similarly, we can find the address for three-dimensional array. In similar way, if size of array is m, n, up p, up to size whatever is n dimension, then if you want to find the address of I, j, k up to whatever is z, then if this is I, this is j, this is k, and this is z. Now if you want to find address according to row measure order, then it will simple go through left to right. First base address plus I minus lower bound of I, that is LB1, multiply by remaining size of element, that is NP up to X. NP up to X plus J. J minus lower bound for J is LB2, multiply by elements right side to the J, that is P, into remaining elements up to N, multiply by remaining elements up to the end, plus similarly K minus lower bound of K, suppose this is 3, then multiply by remaining elements whatever is dash dash up to X plus up to last element is if Z, then Z minus lower bound of last one is N, then there is no other elements at the last, then multiply by the size of it. Similarly, if you want to calculate column measure order, then for n dimensional array, column measure order, A, I, J, K, and if size is X, then and if your matrix is A, M, N, P X, here suppose this is K, then it will calculate it as base address plus, it will find out from right to left. Suppose here if you has lower bound for this one ij, suppose this one is for k, ijk z, suppose this one is z, the z minus lower bound of this one is suppose n, lower bound n, multiply by remaining elements from here up to remaining element, and last one is m into n into p plus this one is for k minus lower bound of this one is if 3 multiply by remaining elements m into n plus I, j, k and z, j minus lower bound 2 multiply by m plus I minus lower bound 1, no remaining elements, and multiply by depth of one element, size of one element. So this is all about calculation of n-dimensional array. This is the references from where I have taken these contents. Thank you for listening.